have so far seen about basic stoichiometry, mass balance. We should have also seen energy balance, but yeah, we couldn't do it last week. So there is one question on energy balance to start with, and then we'll move on to enzyme kinetics and enzyme inhibition. So that is the overview for today. So if you have any doubts from any of the lectures from all the 3 weeks, you can post in the chat box anytime. So I'll read them and answer. And if you also have any comments or suggestions, you are also free to post them as well. So first I'll just share my screen. I hope the screen is visible, and as well as the audio is also clear. If there is any issue, you can let me know. Okay. So yes, we are in the third week of live practice session for this course, and you might have seen me for the past 2 weeks. To introduce again, I am Guru Priya Ramesh. I am a Primary Research Fellow in the Department of Civil Engineering, IIT Madras. And yeah, I have my bachelor's and master's in biotechnology, and now I'm currently working on anaerobic digestion for organic waste stream. With that little introduction, the week 3 course content, as we saw, is on enzyme reactions, the reaction rates, and inhibition of those enzyme reactions. But in the last week we were about to see about some questions on energy balance. So here it's just a very basic one question on energy balance. You can try to solve this now, and in the meantime, if you have any questions regarding this energy balance, any specific doubts, you can also post that in the chat box. So here microbial reactor operates at a steady state, and using the steady state energy balance, you are asked to calculate the heat of reaction, the heat removal requirement, and whether there is cooling required in this condition. So you have to find out del H reaction, Q, and then whether cooling is required. So for that, all the necessary data is given below. So based on this, you can just work out. So like the previous 2 weeks, we will just continue with solving some problems. First I'll post the questions to you, give some time for you to attempt those, and then we will have a round of discussion on the answers. hope you all know the formula for the first one, which is the del heat of reaction. So it is the sum of your heat of reaction, heat of combustion values of the substrate into their mass minus the total sum of the heat of combustion of the product into its mass. So mass into del Hc, heat of combustion of the substrate, and substrate includes all the substrates that would have been used there, minus the same for all the products. Did anyone solve for del heat of reaction? So all you have to do is you have substrate, you have nitrogen source, and you have your product. So here the only product based on the data is the bacterial biomass. You have no other product, right? So in that case you just have to multiply the factors, like 5 into minus 115 plus 0.2 into minus 30. So, and this will give you have to add for these two and then do the same for this. So the biomass production is 1.5 gram per minute and the heat of combustion is 23.2 kilojoule per gram. So when you multiply these two, you will get the M into del Hc for your product. So you have to add the substrate and nitrogen source and subtract the value of the M del Hc of the bacterial biomass. Any answers? try and solve the problems. Like even if you have found the del H reactions, you can just post that value in the chat box and then continue doing for the heat removal requirements basically. Okay, so as I told you, the del heat of reaction is 5 into minus 115 plus 0.2 into minus 30 minus 1.5 into minus 23.2, and that will end up giving you minus 546.2 kilojoules per minute. I hope you got this answer. Any doubts or confusions in this? Did you get this? So this is the del heat of reaction. Next we go on to calculate the heat removal requirement or the heat loss. So the formula that so the formula that you have to be using here is the steady state equation, steady state energy balance equation. So here minus del H reaction minus mv del hv minus q plus ws is equal to 0 is the equation that you have to use. So you already know what is your del H reaction is, okay, and then in the equation you have your minus mv into del hv. So your mass of water loss and the latent heat of vaporization. So both the data is given here. You have your latent heat of vaporization and you have how much of water is evaporated. So this is the m and this is the del hv value. The equation says that when you add the work that is done here, so what is the work done here? The work done is the shaft work supplied to the reactor, which is 10 kilojoules per minute. This will give you the Q. So at steady state the equation is minus del H reaction minus mv del hv minus Q plus ws is equal to 0, but now we have to find q, so you just rearrange it this way: minus del H reaction minus mv del hv plus ws is equal to q. Del H reaction you have found in the first question itself, so that is this minus 546.2 kilojoules per minute, and your mv del hv is what you account for the water loss. mv is the amount of water that is evaporated, which is 0.1 kilogram per minute, and your del hv value, which is the latent heat of vaporization, is 2257 kilojoule per kilogram. And then your ws is the work done. So here the shaft work that is applied is 10 kilojoule per minute. Just apply this in the equation and find out the value of q. If you have found out the value, please post in the chat box. I have given you the values, the equation, you just have to substitute and give me the answer. Trying to solve the question, like if you are trying, then I can wait for you, or else we can continue. I see no response in the chat box. Like, first of all, am I audible and are things smooth with the meeting? Any response? Because from my end I see that my audio is on and I am presenting the screen. Okay, finally. So yes, the Q value is 330.5 kilojoule per minute. So here it is minus del H reaction, so make a note that you should have taken it as 546.2, and yes, the value is correct. So based on that, the third question, whether the reactor cooling is required under this condition. What do you think, whether you need cooling or no? So yes, we need cooling in the system, because what is your Q term? Your Q term tells you what is the heat loss, and that term is basically positive, which means there is heat loss from the system. So you will need a cooling system to remove the heat loss, which is the 330.5 kilojoules per minute, whichever is heat is getting generated, has to be removed, and hence you need a cooling system. So the answer is yes. since we have all problems, like I don't have the solutions attached here, when I upload the PPT as in I will give it with the solutions. But right in this presentation now, I just have the questions and I can help you solve the questions the way I did for this. Okay, so with that, that question on energy balance is done. I think that's the basics of energy balance. One more concept that you have with energy balance is heat of reaction with oxygen as electron acceptor. In that case, it is easy because you have one more equation to find your del Hc, which says that del Hc naught is equal to minus q into degree of reduction into the number of carbon atoms. So you have to see in the question like whether which is the electron acceptor, and based on that you can proceed. So yes, with that we move on to the enzyme catalysis part. So enzyme catalysis, basically we are going to deal with rate of reaction, because the key role of enzymes in bioprocess systems is to increase the rate of the reaction, which means they help accelerate the reaction, but they have no influence on the equilibrium. So they are just catalysts that work on improving the reaction rate, but they have no influence on the equilibrium. So we all know that the enzymes are basically proteins mostly. Apart from that, we also have ribozymes, and then because it's protein, it's going to have a amino acid sequence, and which will have its primary, tertiary, secondary structures. So basically your protein is going to be a tertiary structure where it's going to have all the folds and stuff. So based on these folds only, the active site of the enzyme is decided, and hence the function of the protein itself is decided. So when we talk about enzyme catalysis, how it increases the rate of reaction is that it decreases the activation energy. So activation energy is the minimum amount of energy that you would require for the reaction to proceed. When there is a catalyst, this activation energy is lowered, and hence the rate of reaction is enhanced. So the basics of all this enzyme catalysis is one equation that we call as the Michaelis-Menten equation. So in any enzyme catalyst reaction, you know that you will have an enzyme, you will have the substrate, both together. Directly you will not get the product. First there will be an enzyme substrate complex formed, right? The enzyme and substrate will interact, and then the product will form. So that is the basis of any enzyme catalyst reaction. So based on that, you all know what a Michaelis-Menten equation is, how it is derived, and practically in what all formats you use them. So you also know the assumptions of the Michaelis-Menten equation, supposedly, right? So in case of Michaelis-Menten equation, we assume that there is negligible reverse reactions where the product forms a substrate, and a single enzyme substrate complex is formed and broken, and the substrate is in excess. So these are the assumptions. And then we also have the Briggs-Haldane equation. So in Briggs-Haldane equation, the fact that the K is defined a bit differently, because they assume quasi steady state process. Okay, so quasi steady state means the change of intermediate concentrations with respect to time is assumed to be negligible, which is what is the intermediate concentration here? The ES, enzyme substrate complexes, are the intermediates here. So dES by dt is equal to 0 is assumed, and based on that you have a little variation in the K. So this is the basics of enzyme catalysis, and I hope you know what is turnover number, enzyme activity, and enzyme unit. These three are very basic terms that you should be knowing. Yes, and then you have your catalytic efficiency as well. So all this I hope you know now. And to make things easier, you will go for double reciprocal plot of the Michaelis-Menten equation, where you have the Lineweaver bulk plot, Eddie-Hoxsey plot, and Hainsworth plot. You use it, the different plots, to find out the kinetic parameters. And then you might have seen about the enzyme inhibition. So the inhibition happens when you find that the rate of the enzyme catalyst reaction is reducing. It means that there is a molecule that does that, and that is called the inhibitor. And your inhibition can be a reversible inhibition or an irreversible inhibition. Predominantly the reversible inhibitions that we know include competitive, non-competitive, and uncompetitive inhibitions. I hope you know the difference. We will also see some questions based on this and try to understand them. Apart from that, you have your substrate inhibition as well as the allosteric inhibition. So these are the different kinds of inhibitions that you can study. So with that basic little introduction, I have already presented the question. Maybe you might have read it by now. So two enzymes catalyze the same reaction under identical conditions. So for both, you have to calculate the kcat value and the kcat by km value. So you are given with Vmax, enzyme amount, molecular mass of the enzyme, and the km value. So you have to find the kcat and also find the kcat by km. You are already given the km value. That is the first part. And next, you have to tell which enzyme is intrinsically more efficient at low substrate concentration. And third, you have to find out which enzyme gives the greater total rate under substrate saturating conditions. So you have to assume substrate saturating conditions and find the V in both, for both the enzymes, and comparing the values, you have to tell which gives a greater rate. I will again wait for a few more minutes. If you are done with any part of the question, just start posting it. If you find kcat by km, just start posting it. And if in case you don't know how to do it, after waiting for a couple of minutes, you can just post that as well, so that I know that you don't know, you're not solving it, and I'll right away start explaining the question, answers for the question. first of all, to find out the kcat, I hope you all know the formula for kcat. Kcat is Vmax by total moles of enzyme. So in this table you are given with the Vmax value, but you don't have your total moles of enzyme, but instead you have the molecular mass in kilodaltons. So you just have to convert it to moles. So ideally 1 kilodalton is equal to 1 gram per mole, and you also have the enzyme amount. So with that you can find out what is your moles of enzyme. So note that you are given the mass and the molecular mass. You have to find the moles, which is mass by molecular mass. So mass you can take directly. The molecular mass, you just have to know that 1 kilodalton is equal to 1000 gram per mole. And then you will get to know what is the molar concentration of enzyme A and enzyme B. With that, kcat is equal to Vmax by total moles of enzyme. So you have the Vmax value and the total moles of enzyme, and then you can find out what is the kcat value. And remember, your turnover number is going to be in the units of time inverse. So using these two values, find the moles first, and then your kcat will be the Vmax by that moles. And yes, as posted by Pia, the answer is 8000 per minute for A, which means 8000 molecules are converted to product per minute by enzyme A, whereas with enzyme B it's 7500 per minute. And then when you talk about kcat by km, it's very simple. You have your kcat, you just have your km values, it's just basic division, and it is 4000 per minute for enzyme A and 750 per minute for enzyme B. Is everyone clear with how to solve question A? So it's just finding the number of moles, and Vmax by that moles will give you the kcat, and that kcat by km you can just divide and get this value as well. So based on this value, now you know that A has a kcat value of 8000 per minute and B has 7500 per minute, and the kcat by km ratio is 4000 for enzyme A and 750 for enzyme B. So with these values, now you have to tell me which enzyme is intrinsically more efficient at low substrate concentration. So at low substrate concentration, the factor that determines this is your kcat by km ratio. So A has a greater kcat by km ratio, which is nearly 5 times the increase. So A is more efficient than B at low substrate concentration, because at low substrate concentration you will compare your kcat by km value, and your km is in the denominator, which is the affinity factor, which tells you about the affinity. So the more the ratio, the greater the efficiency at low substrate concentration, and here based on that A is more efficient. Finally, which enzyme gives the greater total rate under substrate saturating conditions? You just have to identify what is substrate saturating conditions. When talking about this enzyme catalysis, you have two conditions. One is the substrate saturating conditions, and another one is the substrate limiting conditions. So to put this in other terms, when your substrate is excess or S is very greater than Km, what would happen? Exactly. So when your substrate is going to be in excess, the rate of the reaction is going to be your maximum rate of reaction. And directly you can compare from the table that the maximum rate of reaction for B is greater. So enzyme B gives the greater total rate under substrate saturating conditions. It's just the same question put in a different wording. So first we saw about substrate limiting conditions, which means enzyme A shows greater affinity to the substrate. So the implications that you can get from such examples is enzyme A has greater affinity to the substrate, whereas enzyme B is a very fast processing system. So when you have a high substrate concentration, the maximum reaction velocity is going to be high with enzyme B. I hope this question was clear. You just had to find out some basic stuff, and then you have to interpret it based on whatever you have found out. Been two conditions. One is at the low substrate concentration or the limiting concentration, and next is at the excess substrate or substrate saturating conditions. doubts, or if you want me to repeat, you can just post in the chat box so that I will repeat. Here is the next question. So there is a rate data from a reaction. So based on this, can you identify which type of inhibition is most consistent with this data? We know different types of inhibition, we have seen them. So seeing the data, can you identify which type of inhibition? And why does the inhibitor have a strong effect at low substrate concentration but a weak effect at high substrate concentration? You should also suggest an effective strategy for reducing the inhibition. If you just find out the answer for first question, I think the rest too follows. You would have seen them. Given is the velocity or the rate data, and the units are micromole per minute. Right, exactly. It is competitive inhibition. The question itself carries the answer in it. So first, when you see the data, when there is 1 millimolar of substrate, which is low substrate concentration. At low substrate concentration, without inhibitor, the rate is 20 micromole per minute. Whereas with inhibitor, it just reduces to half, which is 10 micromole per minute. But when the substrate concentration is so high, as much as 100 millimoles, you can see that without inhibitor the rate is 91 micromole per minute. With inhibitor also it is not very low. There is difference, but it's not as that we saw in the case 1. It's just 89 micromoles per minute. This is a characteristic of typical competitive inhibition. So what is competitive inhibition? The inhibitor is going to directly compete with the substrate for its active site. The enzyme will have an active site in which your substrate should bind, but instead of your substrate, your inhibitor will go and bind to that site, preventing the formation of the enzyme substrate complex itself. So that is competitive inhibition. Okay, so in that case, we know that when the substrate concentration is going to be very excess, then it can overcome this competitive inhibition. So that is what we typically observe here. When the substrate concentration is very low, the substrate cannot actively compete with the inhibitor to reach the active site of the enzyme and make the reaction continue. But when there is a very much excess of your substrate in comparison to your inhibitor, the chances of the substrate binding to the enzyme is very high. The second question will help you answer both the first and third questions. That is the strategy that you have to use. You have to use a very high excess of substrate to overcome the competitive inhibition. I hope it is clear. There was nothing to calculate in the question. It was just data. You observe it and give your inference. The next question is, an enzyme has the following parameters in the absence and presence of inhibitor. So without inhibitor, your Vmax value is 120 micromole per minute and your Km is 6 millimoles. And with inhibitor, it changes to 60 micromoles per minute and your Km changes to 3 millimoles. You again have to identify the inhibition type, calculate the factor that is asked here, and then determine the rate in the presence of inhibitor at a substrate concentration of 3 millimoles. I hope you are following with the questions and the answers. If you have any doubts and if you want me to repeat any of those, you can anytime post in the chat box. Could you also mention the reason? Exactly. So in uncompetitive inhibition, you know that both your Vm and Kmax values are getting lowered. So you can see that the Vmax is reducing by a factor of 2 and your Km is also reducing by a factor of 2, which is a typical scenario in which uncompetitive inhibition happens. So what is uncompetitive inhibition? Where the inhibitor is going to target your enzyme substrate complex itself. Only the enzyme substrate complex is going to get affected. So now you have to find the value of 1 plus I by Ki from the given data. Exactly. So when you talk about uncompetitive inhibition, so we all know what is our Michaelis-Menten equation, that is V is equal to Vmax S by Km plus S. But when we talk about uncompetitive inhibition, your Vmax is going to be sorry uh, so your Vmax apparent will be your Vmax by the given factor, that is 1 plus I by Ki. So now you have to find 1 plus I by Ki, which is the ratio of Vmax by Vmax apparent. You have your Vmax is 120 and your Vmax here is 60 and the factor is 2. So here the factor is 2. And when you compare these two, both V and K is changing, so it is uncompetitive. Okay, and determine the rate in the presence of inhibitor at S is equal to 3 micromoles. It's direct substitution where V is equal to Vmax apparent. What is that Vmax apparent here? It is 60 and your substrate is given as 3 millimolar, and again your Km apparent, which is 3, and your substrate, which is again 3. So if you're directly substituting in this, the rate is going to be 30 micromoles per minute. So the inhibition type is uncompetitive, the factor is 2, and the rate at S is equal to 3 micromoles is 30 micromoles per minute. I hope this is clear. Okay, so the next question. A mutant enzyme has the following properties compared with a wild type enzyme. So you have a wild type enzyme and a mutant enzyme. You're going to assume that they are at identical concentrations. So at identical concentrations, the Km value of the wild type enzyme is 2 millimoles, whereas for mutant it is 1 millimole. And the Vmax is of the wild type is 100 micromoles per minute, and for the mutant it is 60 micromoles per minute. You have to tell whether the mutant binds the substrate more effectively, and the clue here is based on Km value. I think this question is pretty direct and simple. if you compare, we all know that Km value indicates the substrate binding affinity. An enzyme which has a lower Km value has a greater affinity to the substrate. So that is the significance of Km value. Km is the Michaelis-Menten constant. Okay, so comparing the wild type and the mutant type, the mutant has the low Km value, and hence it has higher affinity towards the substrate. So the mutant enzyme will bind more effectively to the substrate. And next, talking about the turnover number, again the kcat value. So the turnover number has a formula of kcat is equal to Vmax by total enzyme concentration. So here you will have to find it based on Vmax by your enzyme, but it is given that the concentrations are identical, the enzyme concentrations are identical. So if this factor is going to be the same, then the only difference is going to be your Vm. You have to directly compare your Vm values given in the table, and the wild type enzyme has a higher turnover number than the mutant. So which enzyme has a larger kcat? It is wild type. And how did we end up? Because kcat you have to determine based on Vm by enzyme concentration, and it is given that the enzyme concentrations are identical, which means you are going to divide it using the same factor. So in that case you can directly compare the Vm values itself. So, and the third question asks us which enzyme has greater catalytic efficiency. Catalytic efficiency is kcat by Km. So here, since again here also this condition applies, the enzyme concentrations are identical. So instead of kcat by Km, you can compare Vmax by Km. The same thing that we did here. Enzyme concentrations are similar, so you can compare kcat instead of kcat by Km. You are just comparing Vmax by Km. So which is 50 here and it is 60 here. So obviously kcat by Km of the mutant is higher. So here your mutant has a greater catalytic efficiency. And similarly, when you talk about the final question, where they have given that the substrate concentration is 0.5 millimoles. So again put it in the normal Michaelis-Menten equation. V is equal to Vmax is by Km plus S. So based on your Vmax and Km value, if you have solved for it, you would know that your rate is going to be 20 micromole per minute for both the enzymes. So at a substrate concentration of 0.5 millimoles, both the the enzymes are going to show a similar rate, which is 20 micromoles per minute. Is it clear? So here I have not mentioned what it is, but by seeing the equation I think you will be able to find out about which condition we are talking about. An enzyme follows V is equal to Vmax S by Km dash plus S square by Ks1. So based on this equation, you first have to identify on what context we are talking. So in that you are given with your Vmax, Km dash and Ks1 value. So determine the substrate concentration that gives maximum velocity. Very simple question. You are given with the equation and the values as well. You just have to identify the substrate concentration that gives maximum velocity. So in this given equation you just have to apply your V is equal to V max. So which will give you, one second, so here this is also V max. That is what we are asking. Like we are telling that the velocity is the maximum velocity, which means V is equal to V max. So in that condition what will happen, you can even do the derivation directly here. If you do that, you will end up getting your substrate concentration to be the square root of your product of Km dash and Ks1. So in our case it is just square root of 400, which is millimoles. So the substrate concentration that gives the maximum velocity is 20 millimoles. Equation is given here. You might remember when we studied about substrate inhibition, we will come across this equation. So this is a characteristic equation of substrate inhibition. Okay, even if you don't remember the fact that S is equal to at maximum velocity, S is equal to root of Km dash into K is 1, you can directly do it from this equation itself. You just substitute V is equal to Vmax, and then you will end up with this equation, and based on the given data, you will know that at maximum velocity, at the substrate concentration of 20 millimolar, you will see the maximum velocity. Similar question, this is another case where the kinetics followed is based on Vmax T equal to Km ln S naught by S plus S naught minus S. So last question was about substrate inhibition, and in this question we have another type of inhibition. So here you have given with the Vmax and the Km value, you have to calculate the time required for the substrate to decrease from 20 to 10 millimolar, and for the substrate to decrease from 10 to 2 millimolar. Equation is given, all the required data is given. You just have to find out how much time it takes for the substrate to come from 20 to 10 millimolar and from 10 to 2 millimolar, and you have to compare these two values, which takes the longer time interval and why. In order to solve any question related to bioprocess, you basically have to know what assumptions are made in that condition. If you have to know the basic equation and that basic equation with the assumptions, and then you have to know the variations in those equations. So if you are thorough with that understanding, then solving any problem in bioprocess is going to be easier. I hope I was not fast with the previous question. It was very simple based on substrate inhibition. Now you can try this. If you want me to repeat that question, you can just post in the chat box so that I'll go back and repeat. Hope you recognize this equation. This is just your basic Michaelis-Menten equation. V is equal to Vmax S by Ks plus S. So when you need to solve for kinetic parameters using your Michaelis-Menten equation, you will substitute your V with the factor called minus ds by dt. What is your V? It is the product found over time or the substrate consumed over time. That will give you your velocity, right? So instead of V is equal to Vmax S by Km plus S, you will just have minus ds by dt is equal to E max S by Km plus S. And then when you are going to do the integration for that reaction, what you end up is this equation. Because the practice session is not meant to test your memory, I am giving all the equations right away here and then asking you to solve. The only tricky part here is the interpretation. So based on how well you have understood the concept, you can do your interpretation. Okay, so if you are directly substituting the values uh, is not 20 and S10 in the first case and S0 10 and S2 in the second case, the values for the time required is going to be 3.54 minutes for conversion of 20 millimolar to 10 millimolar, and then it's going to be 4.91 minutes for conversion from 10 millimolar to 2 millimolar. So So the answer Pia has given is completely right. It's just direct substitution and you will get these two values, and comparing these two values, it's very obvious that 10 to 2 millimolar takes longer time. You are just going to compare two values and say which is greater. That's fine. But the important part is this y. So when you substitute, you get 3.5 here and you get 4.4 here. And we have mentioned that it is going to be Michaelis-Menten kinetics. So if you take a closer look at the Michaelis-Menten kinetics, you will going to see this pattern. And when let's say here you have your Vmax, this would be your Vmax by 2, this would be your Km value, this would be your Km value. So you know what this plot is, you know what is Vmax here. You also know here it is going to be a first order and here it is going to be a zero order, and the reason is here you have excess substrate. So substrate is going to be very excess, and there is going to be independence of the rate on the substrate after some point. So this is a basic concept that you already know, right? Based on that, in the first interval, which is conversion from 20 millimole to 10 millimole, the substrate concentration is mostly above your Km value. What is your Km value given here? It is 6 millimoles. 20 and 10 millimole is obviously greater than 6 millimoles. So it operates at the near maximum velocity, obviously. Okay, and it is also independent of concentration at this point when you try to graphically understand this. But when you talk about the second case where it has to fall from 10 to 2 millimolar, the substrate concentration is going to significantly fall below your Km value. So this is where the enzyme is not going to be saturated. So in the first case your enzyme is going to be saturated, but in the second case the enzyme is not going to be saturated. So here the reaction rate is going to drop. As you can see in this below Km, you can see your reaction rate here at this point is going to drop. So I hope when you see a problem, look at the values, try to compare and try to understand why it happens. So here you can just see a direct shift from the system arriving from a zero order reaction to a first order reaction. When the concentration is high, it behaves like a zero order reaction and the rate is going to be high. But when you come down, the substrate concentration has a greater effect on your V value and then it's going to decrease. Okay, the next question is, we have a experiment where E naught value is 0.1 millimole and the S value is S naught value is 0.05 millimoles. Okay, total enzyme and the initial substrate concentration are given. So here the investigator assumes that the substrate concentration remains constant during the initial rate period and he is applying the standard Michaelis-Menten equation. Is it right or wrong? And based on your understanding of the assumptions of Michaelis-Menten equation, answer the given questions. It's just basically a reasoning question. There is no calculation or formula involved. assumptions of the Michaelis-Menten equation? If you remember that, you can answer this. I had mentioned 3 assumptions. So the basic assumptions of any Michaelis-Menten equation is that there is negligible reverse reaction where the product forms substrate. That is first. Second is there is single enzyme substrate complex formed and broken. Third, and the most important for this question, is that the substrate is in excess. Only when the substrate is in excess we can tell that the substrate is nearly constant, like even though all the enzyme is bound with substrate, you still have a large amount of free excess substrate left in the system. That is one of the most important assumptions of the Michaelis-Menten equation. You can't apply to all conditions, but with the given data it is very clear that your enzyme concentration is twice as the substrate concentration. So that's the key assumption that was violated before assuming a Michaelis-Menten kinetics for the given reaction. And the second question is, why can the measured rate no longer be interpreted as a true initial velocity under the usual approximation? Because in usual approximation only when there is excess substrate we will like have the enzyme substrate complex formed stably over a measurable period in the system. When there is going to be very less substrate, then right in the beginning of the reaction itself all your enzyme is going to be bound with substrate, and even there are going to be enzyme molecules that are not bound with substrate, and then your substrate is going to be rapidly converted into product. So this is, there is no steady state of enzyme substrate complex, there is no such concept here in this situation, and hence we cannot consider the measured rate as the true initial velocity. So to validate this system, the one experimental modification, by now you would have guessed that you have to increase the substrate concentration considerably so as to comply with the third assumption of the Michaelis-Menten kinetics, or you can significantly decrease your enzyme concentration. So anyhow you have to bring your substrate to be in excess to your enzyme, add more substrate or remove enzyme such that the S naught is very greater than your E naught. So this is the very basic concept of Michaelis-Menten equation. You have to know the assumptions, and then only you can identify in which conditions you can use those equations. The next question is for an enzyme catalyzed reaction. The activation energy is 50 kilojoules per mole. Increasing the temperature from 300 Kelvin to 310 Kelvin would increase the intrinsic rate constant according to the Arrhenius equation. However, the active enzyme also deactivates at the same time using the given equation, which is EAT is equal to E naught into e power minus kdt. And here the constant for enzyme deactivation is 0.1 per hour. So I want you to calculate the Arrhenius rate constant ratio, which is K310 by K300, and calculate the fraction of active enzymes remaining after 5 hours, and explain why the temperature increase may not produce a sustained 5-hour increase in reactor productivity. I hope you know the basic Arrhenius equation, that is K is equal to A e power minus EA by RT. So this is the basic equation, but in our case what we would need is very simple. You will have these integrated into EA by R into 1 by T2 minus 1 by T1 is equal to ln K1 by K2. Now whatever is asked here is this. So, and all other things are given here. From that you just have to substitute in this formula and find out this ratio. Okay, so because we are at near the end of the session, I will just explain the answer for this question right away now. um, yeah, so when you substitute, you have given the EA value, you know, for kilojoules per mole. In that case, what R you have to take. When you substitute, your ratio is going to be 1.96. I hope you all end up getting this value after your calculation, but yeah, it is 1.96. Okay, and you have to calculate the fraction of enzyme that is active after 5 hours. So for that you can use this equation, right? This equation. So here the fraction that is going to be active is EAT by E naught, which is equal to e power minus kdt. You know the kd value is 0.1 per hour, the t is 5 hours. Just e power minus 0.5 into e power minus 0.1 into 5 is going to give you a fraction of 0.6, which is around 60%. Around 60% of the enzyme is going to be active after 5 hours, provided that there is also simultaneous enzyme deactivation. Okay, and third question is, explain why temperature increase may not produce a sustained 5-hour increase in reactor productivity. Yeah, when increasing the temperature, we can expect a increase in reactor productivity, but at what cost? That is the question. So this enzyme is also dependent on temperature. Only up to a certain temperature. When you see the relevance of enzymes to temperature, I hope you remember that you would have always read about a bell-shaped curve. Only above up to a certain level, you will see an increase in the performance. After that, it is going to decrease because your enzyme is going to get deactivated. So whenever this Arrhenius behavior is observed, you should also keep in mind that a simultaneous deactivation will also take place. So hence, due to the deactivation, nearly 40% of the enzyme is getting deactivated only, and only 60% is remaining. So it's naturally you can't observe any increase in the reactor productivity, and that is why we talk about optimum conditions for any bioprocess. So the optimum conditions include the temperature, the pressure, the pH, all of this, because they can bring about your enzyme or protein denaturation. And last question is too much out of the scope of this course. I just added that question just to give you an introduction. So you have to consider the simultaneous Arrhenius behavior and the deactivation factors. You have to consider your substrate mass balance. You have to consider what kind of inhibitions can happen. Most importantly, the thermodynamics is going to play a great role here. All these factors and constant when you bring in, then you can bring a realistic model. You can just improvise on the given model. Okay, so the next question we have, I guess we have two more questions. What we are just running out of time now. Okay, so the next question is, an inhibitor changes the kinetic parameters as follows. The Vmax is getting decreased and the Km is getting decreased. As we saw in the first one of the first questions, like the second, third question, we saw about competitive inhibition, uncompetitive inhibition and stuff. So in a competitive inhibition, you know that the Km will increase but the Vmax will remain unchanged. So it is not a competitive inhibition. That is the first question here. When we talk about uncompetitive inhibition, as we saw, both Km and Vmax decreases, but here what happens, your Vmax value decreases and your Km value is increasing from 4 to 8. Therefore it is not uncompetitive as well. So then you talk about another set called the mixed inhibition, where the Vmax will decrease while the Km will increase. Calculate the uninhibited and inhibited rates at S is equal to 4. So it's just direct application of V is equal to Vmax S by Km plus S. You have to apply the corresponding Vmax and Km value and then you will get the answers. Okay. So at uninhibited, you will use this, and for inhibition you will use these two factors. So when you do that, you will find that uninhibited rate is 50 and with inhibition your rate is going to be 16.7. So I have already solved, so I just have the values. It's just 50 and 16.7. You can just calculate yourself and see whether you're getting the answer. So we all know that the inhibitor changes both substrate and response behavior. We know that sometimes it only affects the substrate, sometimes the enzyme only, sometimes the enzyme substrate complex. So it's the inhibitor is not targeting either the substrate or the enzyme. So in that case, only Vmax cannot be used as the factor to explain the effect of inhibitor. A reactor initially has a catalytic capacity of 100 micromoles per minute. The enzyme deactivation is given here. Calculate the Vmax after 10 hours. So Vmax T is equal to Vmax initial into e power minus kdt. This Vmax 0 is 100 micromoles per minute, and your kd value is 0.1, and the time is 10 hours. If you substitute, your Vmax value is going to be 36.8 micromoles per minute. So out of 100, 36.8 is going to remain. Okay, so then the lost fraction, okay, let me just write this down quickly. When you are going to directly substitute this value, this here, you will find your Vmax. That is 36.8. Okay, considering this is the fraction that is remaining. Okay, what fraction is lost is, initially there were 100, so the lost fraction is going to be 63.21%. Okay, so you have to add that much. 63.21% has to be added to restore the original capacity. And another question, basically you might have heard that enzymatic processes are costly processes. One major limitation is keep on adding pure enzymes. It gets deactivated at one point, you keep on adding new enzyme, it's going to give a lot of cost. That is one major limitation of using enzyme addition as a strategy for maintaining productivity. So here we see that there is going to be denaturation of enzyme, but in order to keep up the productivity, we propose that okay, whenever it is denaturing, we will add more enzymes. But what happens, it will increase your cost, so obviously it makes no sense here. So you have to go for other strategies. So with that, we come to the end of today's session. I hope it was useful, though I couldn't see much of your interaction. Is there any specific reason for that, where you're not able to follow, where the questions so difficult? If you can let me know, I can prepare the questions or the session for the next week accordingly. Is it fine? Were you able to follow, and was the session useful? A quick question, I expect answer at least for this question now. Okay, one person. And thank you again, Priya, for answering throughout, because the session without people answering would be so monotonous. I just waiting and then explaining. So if you want me to come up with a session where I just explain concepts, that is also fine by me. So if you can let me know in this session, I'll prepare accordingly for the next session, rather than a question answer session, because this works only when there is interaction both sides. Any suggestions, any stuff? Okay, when you talk about this heat of reaction with oxygen as electron acceptor, you are going to find the del H reaction using a different formula, which is minus Q into your degree of reduction into your number of carbon atoms, because when you use oxygen as your electron acceptor, you are going to assume that you're going to find the molar heat of combustion at the standard conditions. So that is why you assume this formula. I am. Can you be little more specific on what exactly you are trying to ask here? You can't understand the formula in the sense.